Start recording. Huh? Now he started. So thank you everybody that this is the final presentation for today. Now is the turn for Elham. Elham is a PhD candidate from Western University. So please, Elham, the room is yours.
Thank you. Hello, everyone. Thanks for your introduction and your kind invitation. Let me share my screen first. Please let me know you can see my screen.
Yeah, everything perfect.
Okay, great. Today I'm going to talk about learning partial differential equation from data using machine learning. In my PhD research focus on using machine learning tools and analytical theory for building physical models for multi-scale modeling. And using macroscopic models and macroscopic properties to describe complex system is common. But when we are talking about macroscopic models like this figure, we don't consider activities at molecular levels, and we don't consider physical and mechanical or chemical mechanisms in full detail. Because of this, scientists resort to microscopic models because they can explain the behavior of the system in full details and consider activities at molecular levels. Some microscopic models like molecular dynamics. What we are doing here is that we are looking for a way that connect macroscopic properties of the system to macro-scale PDEs. When we have a macroscopic or macro-scale data, we are looking for a way that build a bridge between macro-scale and macro-scale both. In my research, for given x and y, we are looking for a function f that explains the behavior of, that explains the relation between x and y. Actually, for x as the input and y as the output, we are looking for a function f that relates x and y. And we can say that y equals f of x. Because we have coarse scale PDEs here, what we are looking for is this kind of equation, and this is exactly the function that we are looking for. And the purpose of finding this function is finding a relation between time derivatives and other space derivatives when we have coarse scale variable. In this research, we are using data from simulation and experiments, and then find the coarse scale variable from fine scale variables. And at the next step, we can find space derivative and time derivatives by finite difference method. And Gaussian process and neural network can be used to approximate this partial differential equation. This is the general form of the partial differential equation. And sometimes, because we have different terms of derivative, it's better to use feature selection that helps us to select some important features for input. One of the methods that can be used here is sparse regression. In this method, after collecting data from fine scale simulation, we can build this library that is very large matrix. The first column of this matrix is 1, and then observation values that are coarse scale variables and their space derivatives. The purpose of this is finding a relation between these variables and time derivatives. A sparse regression here can minimize this function, and finally the output of this sparse regression is a partial differential equation like this one. And the best thing about this method is that it can calculate the coefficient of each parameters here. Another method that can be used here is artificial neural network. A network consists of some layers, input layer, hidden layer, and output layer. And we connect these layers with weights. And for input layer, we can use a formula that is the combination of weight and input to calculate the value of neuron. And then after calculating output, we use cost function. Here is mean square error to check the error of this output. It means that we calculate this cost function by comparing the output and this prediction and the exact value of target value. And then after optimizing this cost function, we can update the value of weights and biases. And then after updating this, we can try to update weight. We can continue this to get the best output. This is the general form of the backpropagation neural network. The method that can be used here is Gaussian process. As I said, for given x and y, we are looking for a function f. We assume that this function has a normal distribution here with 0 mean. Its mean is 0 and k is covariance. And here we use RBF or radial basis kernel function. That's very common kernel function in this method. This is an exponential function that we can use here to find the correlation between inputs. What we are looking for here is finding the mean value of y star. This is exactly what we are looking for, because after finding this y bar that is mean value, this is our estimated time derivative. To evaluate our model, we use two equations, or we have two examples of equations. One of them is heat equation. That's a very simple equation here. This is one-dimensional equation. By considering this initial and boundary condition, we will have analytical solution for this equation. And when we have an analytical solution, we can calculate the derivative, space derivative and time derivative of this equation. This figure shows the solution of this equation. First space derivative of this equation, second derivative, and time derivative of this equation. The purpose of this prediction is finding a relation between this time derivative and other derivatives of this solution. This is the result of neural network prediction. As we can see here, x-axis here is exactly time variable, or the exact value for time derivatives, and the y-axis is time derivative that predicted by neural network. The figure shows that neural networks can approximate the time derivative perfectly. By comparing the result of neural network by these figures, this one and this one, we can see that neural network can predict the equation perfectly. And also, this is the result of Gaussian process that can be used for predicting partial differential equation here. Again, this figure shows that the relation between exact value, exact time derivative values, and prediction values, it shows that the prediction works perfectly on this data. And also by comparing the result of this, by comparing these figures, we can see that Gaussian process can be a good models for predicting heat equation as well. Another equation that I'm going to talk about is phase field model. At first, this is a second order equation. To collect data, we run this model for 20,000 iteration, and the time step is 0.1. The size of this system is 2056 and times 2056. And here is a snapshot of simulation, and this figure shows the value of the macroscopic values and the first derivative times derivative of these macroscopic values and the second derivatives of these values. This is the prediction, Gaussian process regression prediction. As we can see here, the figure shows relation between exact values for time derivative and predicted values, and the figure shows that Gaussian process can predict this phase field equation perfectly. And by comparing the result of the Gaussian process and comparing these figures, we can see that the figures are almost same, and Gaussian process predict the equation perfectly. And these figures shows that the blue points are related to test values for predicting this equation, and the red one are predicted values. And we can see that the predicted values covers the actual values perfectly. Last figures is the result of neural networks for this prediction. For this prediction, we used two hidden layers for prediction, and six neurons at each layer. And loss function here is mean square error, and the activation function is hyperbolic tangent. And the result here shows that the prediction by neural network for phase field is better than the Gaussian process. If we check this one and this one, we see that the prediction by neural network is better than Gaussian process. And by comparing the result of neural network prediction, you can see that neural network can work on phase field equation data perfectly, because we got the same result. This is the exact values, exact time derivatives, and this figure is predicted values, and they are almost same. Thank you for your attention.
Well, thank you, Elham, for your nice talk. I will briefly show you the certificate, and we will start the questions. So I will pretty much say it. The Department of Science and Engineering proudly presents this certificate of participation to Elham Kianiharchegani for presenting a talk entitled Learning Partial Differential Equations from Data Using Machine Learning, held in first annual symposium of the research group in basic science of the Department of Science and Engineering of the Universidad Iberoamericana Puebla, San Andrés Cholula, Puebla, November 11, 2021. It signs the director, the Maestro Ramiro Antonio Bernal Cuevas. Well, thank you. Now we will start with questions.